One new notification from Amazon Shopping. GoPro Hero 7 will arrive today.
Come on.
Don't worry, it's not a GoPro review. I'm finally getting my video toolkit up to speed with a couple of new odds and ends. Up until now, a good bit of my footage had been shot with a Hero session. The original Hero session. Today, we're talking about ports. In fact, I'd like to make this the definitive resource for what's what among waveguides. And then some. Fair warning, I'm going to cover a lot of ground in a short amount of time, so please don't feel like you have to absorb it all in one go. Took me 20 years and I'm still learning. Alright, so let's get a list going. These are the common ways to get pressure between and out of compression chambers. Linear cylindrical vents, flared cylindrical vents, linear rectangular vents, flared rectangular vents, tapered waveguides, compound tapered waveguides, transmission lines, passive radiators, and aperiodic vents. I know it sounds like a lot of stuff, but several of these are just variants of one another, and I'll show you a way of grouping what they do in a way that makes sense. So, let's first talk about the shape of a vent's cross-section. Something that I can't stress enough is the fact that a round vent is not going to behave the same as a rectangular vent of the same area, and that goes for any two shapes. Have a look at this. Here's a rectangular vent that's 5 units tall by 20 units wide. This gives us an area of 100 square units. Next, we have a square vent that's 10 units tall by 10 units wide. This also gives us an area of 100 square units. And finally, here's a round vent with a diameter of 11.28 units, which again comes out to 100 square units. So, as you can see, all three examples have the exact same vent area, but that's about as far as their similarities go. When a fluid, such as air, flows through one of these, peak velocity is achieved around the center. And as we move away from the center, there is a drop in velocity because of the air dragging against the vent itself. So the smaller the circumference for any given vent area, the more efficient or lower drag that vent becomes. And bearing that in mind, let's have another look at our three shapes. The rectangular vent has two 5-unit walls and two 20-unit walls for a total circumference of 50 units. The square vent has four 10-unit walls for a total circumference of 40 units. And for the circumference of a circle, we multiply the diameter times pi, which comes out to... hang on, I'm still doing it. 35.43 units, making it the most efficient way to shape your vent area. And that applies to every type of waveguide. Circular cross-section is the most efficient. The only caveat here is that efficient simply means fast, so for any given tuning frequency, a round vent is gonna have to be longer than any other shaped vent of the same area. And yes, there's a lot more to discuss here once we get into bends and folds, the resulting lateral interference, turbulent flow versus laminar flow, but I'm trying to keep this overview concise so that we can build upon it in the future. So, now that we have the shapes covered, let's talk about flares and tapers.
Flares and tapers, you say, Pete?
Yes, other Pete. Flares and tapers, that was entirely pointless. So the reason I'm grouping flares and tapers together is that they're both used to manipulate velocity and acoustic impedance. In certain applications they're referred to as horns, and the main difference between the large ones like you see in pro audio and the small ones like you see at the ends of port tubes is their relationship to the lengths of waves passing through them. For example, when the size of a waveguide is equal to or larger than the quarter wavelength of the target frequency, acoustic amplification occurs as the pressure traveling outward increases in displacement. On the other hand, if a waveguide is smaller than the quarter wavelength of the target frequency, it is referred to as acoustically small and functions only as a velocity ramp. These are still essential for keeping the vent's air mass intact and preventing chuffing anytime the vent area, or shape, is less than ideal. Incidentally, large flares are often used without any rhyme or reason, especially in car audio, so if you're being sold on one, you might do well to ask your designer for a vent velocity graph, with and without the flare, just to see if it's actually compensating for excessive turbulence or merely taxing the chamber volume and costing more to fabricate. For as long as I've done this, there's only ever been a small handful of projects actually relying on a broad flare at the end of the waveguide. So, building on this, let's have a look at compound tapered waveguides, or if you prefer, two horns joined at the throat. These are almost always going to be acoustically small, and as such, their operation is similar to that of a flared port, minus the linear section. And as you gradually compress, then decompress the airflow passing through, you still achieve an air mass, but with far less disruption at either end, which makes these ideal for high velocity applications. By the way, this does not necessarily mean SPL. More often than not, it means being able to get away with a smaller overall vent volume and, by extension, smaller enclosure. In fact, a lot of the work that I've done for portable speaker manufacturers relies on this very principle. Rather than just slinging a mass of air back and forth like we do with conventional, acoustically small waveguides, transmission lines operate on the principle of phase shift by way of travel distance. And just like in the earlier example, for a waveguide to function as a transmission line, its length has to be equal to or greater than the quarter wavelength of the target frequency. So, while the velocity of a conventional vent peaks out around the system's resonant frequency, the velocity of a transmission line peaks around the time its phase relationship to the driver reaches 90 degrees. In that regard, transmission lines are non-resonant, offering more consistent loading across their operating range. They can also be tapered, which cuts down on their overall volume and slows down the transfer of pressure, albeit at the expense of efficiency. Now then, everything we've discussed so far relies on a confined volume of air. This next thing does not, and I'm talking about passive radiators, or drone cones as they're sometimes called. Functionally, they're very similar to conventional vents, except instead of an air mass, they have a physical moving mass, and their compliance is achieved mechanically by way of suspension, just like with a regular speaker. The main benefit of using passive radiators over regular waveguides is that they don't really take up any space inside the enclosure, and they don't suffer from port noise. On the flip side, at high velocity, their mechanical suspension makes them less linear than conventional vents, which translates to distortion. Lastly, let's talk about aperiodic vents. And while everything else that we've covered bears inductive properties, aperiodic vents have resistive properties. What is an aperiodic vent exactly? Stretch a piece of cloth over your mouth and blow. That's an aperiodic vent. It's a non-resonant air leak that resists the flow of air with little regard for frequency or velocity. You'll typically find these used in undersized sealed enclosures to lower their total Q or to improve the damping without actually increasing the size of the chamber. The trade-offs include reduced efficiency and a slight rise in group delay. So, that's the list. We cover the effects of shape, we cover the effects of flares, we distinguish between flares and tapers.
Flares and...
We did that. Wasn't even that funny. We talked about compound tapered waveguides, transmission lines, passive radiators, and cleaning rags for glasses. I hope you guys enjoyed this video. Be sure to rate it accordingly. If you're not subscribed to the channel, there's a lot of good content you might not be keeping tabs on. Just looking over my project list, lots of sound-related topics that, near as I can tell, no one on YouTube has even touched on yet, and it's all coming down the pike. So, as always, I'm looking forward to your comments. They've been great so far, and they help me sort of plot the course ahead. That being said, I'll see you guys in the next one. Cheers!